Next chapter, heat transfer. Now, let us consider the two blocks we had in the previous chapter. In common language, we say one is hot and the other is cold. And we know that because one has a higher temperature than the other. Now watch what happens when we put the blocks in contact with each other. One is gaining heat and the other is losing heat. Again, we know that because we can see the changing temperatures from the thermometers. What happened is that heat has been transferred from the hot block to the cold one. And this happens until both blocks are at the same temperature. In other words, both have the same amount of heat. Now, in order to understand this concept of heat transfer, we need to first understand the concept of heat and temperature. These are two terms that many people often think mean the same thing, but they actually don't. And it is important as physicists that we get their meanings right as a prerequisite in the study of thermodynamics. So, what is the difference? Most people are familiar with the concept of heat and can describe the sensation of feeling too hot or too cold. But in science, saying something is hot or cold is just not enough. We want to quantify everything that we can. For example, this fire is hot, but this coffee too is hot. However, the hotness is not the same. We need to say how hot something is using numbers. So we measure the temperature. And that begs the question, what is it that temperature is physically measuring? Temperature is measuring the amount of heat energy available in a system. And heat energy is related to the average kinetic energy of the particles in a system. We know that greater kinetic energy means particles will move faster. So higher temperature simply means fast-moving particles. Heat will flow from hot objects to cold objects because as particles move, they will pass their kinetic energy on to other particles through collisions. This will continue to occur until the whole system is at the same temperature in a state we call thermal equilibrium. This is how thermometers measure temperature. Heat from the environment or an object will be in contact with the thermometer and flow into the thermometer liquid, causing the particles to gain kinetic energy, and the liquid will expand until it is in thermal equilibrium with the surroundings, thus allowing us to read the temperature in any of the scales. Remember that all matters expand on heating in what we called thermal expansion. Energy is transferred as heat in a wide variety of processes. When a collision occurs, there's usually some heat generated. Friction can cause heat as well, which is why your hands will warm up when you rub them together vigorously. In this chapter, we are considering the kinetic energy of particles and the transfer of some of this energy to other particles as the definitions of heat and heat transfer. Heat is therefore energy in transit and will be measured in joules just like any other kind of energy. It cannot be measured directly by an instrument. But the transfer of heat energy will always alter the temperature of an object, as heat will always flow from the higher temperature object to the lower temperature object until thermal equilibrium is reached. And this is why hot objects feel hot and cold objects feel cold, because a hot cup of coffee, which is hotter than your hand, will transfer heat into your hand, while a cold piece of ice, which is colder than your hands, will cause heat to be transferred out of your hand into the ice. These events produce the hot and cold sensations that we feel in our everyday life. Now, as we proceed, it is important to redefine the terms particles, which we said make up all matter. From time to time, The word particles will be replaced by more specific terms, atoms and molecules, which you may be learning in other subjects. What we've been calling particles are in fact atoms and molecules. All matter is made up of tiny particles called atoms. Molecules are often used when referring to liquids and gases. In most liquids and gases, two or more atoms join to form a unit called a molecule. So when we say water or gas molecules or metal atoms, just bear in mind that we are referring to the particles that make up matter. Now that we understand all these, let's talk about modes of heat transfer. Now, heat can be transferred by three modes: conduction, convection, and radiation. Conduction and convection require material medium, while radiation doesn't. It can take place even in a vacuum. Conduction mainly occurs in solids, while convection occurs in liquids and gases. We start with conduction. And conduction is a mode of heat transfer in which the material medium doesn't move. Consider these two solids held with the hand on one end, while the other end is placed in fire. One is a metal and the other is a glass rod. In which of the two do you think heat will reach the hand first? Common experience will tell you that it is the metal rod. And that is because metals are better at conducting than glass. Glass still does conduct heat, just not as well as metal. But what makes metals better conductors than glass, yet as you can imagine, they are both made up of atoms? Let's look at the atoms in glass and see how it conducts. Glass is a typical solid in the way it conducts. The particles by the fire start to gain heat from it and they vibrate much more vigorously. They collide with particles next to them, passing on the energy, and slowly along the rod, each atom vibrates more vigorously, passing on heat to the next one through collisions. This progresses slowly through the glass. This is how conduction occurs in most normal solids, and this is why solids are good at conducting heat, because the particles are so close together and they collide very often. And so at the molecular level, conduction is heat transfer through collisions of energized particles. Now let's look at metals and see why they are better conductors than glass. In metals, the same process is happening as in glass. The atoms near the fire gain heat, vibrate, and collide with those next to them. But there's something else happening in the metal. There are free electrons jetting around. We call them free delocalized electrons and are released from the metal atoms. They can collide with other particles in the metal, so they get heat from the hot end and race straight on, bumping on the atoms in the cold end, therefore spreading the heat through the metal much quicker. This is the added advantage in metals, which makes them better conductors than other solids like glass, wood, rubber, plastic, and so on. Now, let's think about this. When it is cold, which chair would you prefer to sit on? Metallic or wooden? Probably wooden, because the metal chair feels colder, right? What if I told you that both of them are actually at the same temperature? Would you believe it? Probably not, but you should. And let's see why. First, we've said that the sensation of hot or cold really depends on whether your body is losing or gaining heat. Gaining heat is interpreted as hot, while losing heat is interpreted as cold. When you sit on a wooden chair, your body loses heat slowly because wood is a poor conductor of heat. But when you sit on a metal chair, with metal being a good conductor of heat, your body loses heat much faster to the metal, which also conducts it faster. This fast heat loss is translated as very cold. Now, think about this on your own. You have two bowls, one is metallic and the other plastic or wooden, both at room temperature. If you put pieces of ice cream on each bowl, which piece will melt fast and why? Think about that. Now let's talk about comparing thermal conductivities of various metals. Consider these pieces of metals: copper, aluminium, brass, and iron, with equal amount of wax placed on one end. The other end is heated with a Bunsen flame. The melting of the candle wax will give an indication of which metal conducts faster than the rest. Copper is the first one to go. The wax is melting after 30 seconds. Aluminium is starting to melt after 45 seconds or so. Brass is following after about 80 seconds. And obviously, iron will be the last. And so in terms of the order of increasing conductivity, we can have it like this. Iron is the worst. Brass is better than iron, aluminium is better than brass, and copper is the best of the four. Now, all metals have tightly held atoms and free electrons. So why does conductivity vary among them? Well, it's got to do with the number of delocalized electrons. Metals with higher numbers of delocalized electrons will have better conductivities than those with less. So the factors affecting thermal conductivity include the nature of the material, which we have discussed, length of the conductor, cross-sectional area or thickness of the conductor, and temperature difference between the ends of the conductor. We shall look at the mathematical relationship of these factors in Form 3, but for now, let's look at the other three factors. We start with the length of the conductor. Now, consider this metallic bar held on a stand. We attach iron nails on the bar using candle wax. Then hit one end of the bar with a candle flame. The rod gets heated and slowly the nails fall down one by one, starting with the one closest to the flame. This demonstration shows that conductivity depends on the length of the conductor. Heat flows from one end to the other, so the farthest nail from the candle will fall last. And this is because the heat covers the longest distance and needs to energize the highest number of atoms. Furthermore, a longer length means a large surface area exposed to heat losses. This is why lagging materials are used on metals, so that heat travels along a straight path with minimal losses. Next, cross-sectional area or thickness of the conductor. Now, consider two pieces of aluminum rods of the same length but different thickness, with two pins attached on one end with wax and the other ends heated with a Bunsen flame. Which pin do you think will fall first? You will see that the pin attached to the thicker rod falls first, and this means that conductivity increases with thickness. And this is because the number of free delocalized electrons per unit length of the thicker metal is more than that of the thin rod. Finally, temperature differences. Consider two conductors of the same material having the same length and thickness, one placed in a flame and the other in hot water. Which one gets hotter first on the other end? It is the one placed in the flame. Both ends of the metal start at the same temperature. but the flame is hotter than the water. So the difference in temperature between the two ends in setup A is greater than in B. This difference is called thermal gradient. The larger the gradient, the faster the conduction. Two very common applications of thermal conductivity is insulation of cooking utensils and the use of heat sinks in integrated circuits and transistors in electronic devices. Cooking utensils are made of metals which conduct heat rapidly. The handles are however made of or coated with insulators such as wood or plastic. Thermal management is important when dealing with electronics. A heat sink is a heat dissipation device that consists of a base and fins that extend outwards. When a chip heats up, a heat sink removes and disperses the heat to keep the chip at a proper operational temperature. The mechanism is by conduction, convection, and radiation. The heat comes into the fins and then the flow takes it away. Without the use of heat sinks, the chip can overheat, which would damage the entire system. The most commonly used material in thermal sinks is aluminum due to its good thermal conductivity. Copper is sometimes used due to its excellent conductivity, but it is usually expensive. In buildings where the inside temperature needs to be stabilized, double walls are constructed with insulators and materials that can trap air put in between the walls. This prevents excessive heating or cooling of the house. Double-glazed windows also trap air in between, which is a poor conductor of heat. So much for solids. Let's look at thermal conductivity in liquids. Now, we put some ice cubes at the bottom of a test tube with water. Place a net wire above the ice to prevent it from floating. The test tube is secured on a clamp in an inclined position. We hit the test tube near the mouth. Water at the top starts to boil while the ice cube remains unmelted. And this is because water is a poor conductor of heat. Heat or thermal energy from the heated water at the top is transferred to the ice cube very slowly. So the water at the bottom remains cold for a long time. So what makes water and indeed liquids poor conductors? We said conduction is thermal transfer through collisions of vibrating particles. But in liquids, the particles, in this case molecules, are far apart, making it hard to pass on their kinetic energy to each other. How would you expect conductivity in gases to be? Negligible. The molecules are much far apart, meaning the passing of kinetic energy is almost impossible. Consider a matchstick being moved vertically along the edge of a Bunsen flame. Even though the matchstick is only about half a centimeter away from the flame, it doesn't ignite, and that shows air is a poor conductor of heat. If you brought the matchstick downward like this, it will ignite instantly. And so, how then do liquids and gases transfer heat because conduction is almost negligible? In science, liquids and gases are collectively called fluids. In other words, states of matter that flow. Thermal conductivity in fluids occurs through convection. Unlike in conduction, Convection involves the movement of the medium of heat transfer, that is, actual movement of the fluid. Now, consider this beaker with water placed on a tripod stand. We drop some crystals of potassium permanganate. We heat the beaker and watch the movement of the colored solution. The colored solution rises up, and when it gets to the top, it spreads out and starts to sink again along the ends. This movement forms what we call convectional currents. Let's see how they form. When water in a beaker is heated, the bottom of the container absorbs heat from the burner and then conducts it to the water. Since the entire body of water is not in contact with the bottom of the container, all the layers of water cannot absorb heat by conduction. The water in contact with the bottom of the container absorbs heat by conduction and its temperature increases. This causes the water to expand and hence its density decreases. This low-density warm water rises up towards the surface because it's lighter than the cold water. The denser cold water moves down and comes into contact with the hot container base. This water gets heated, expands, decreases in density, and rises and is equally replaced by a cooler part of the water in the container. This sets up convectional currents, and this way all the water gets heated. This heat transfer by actual motion of matter from one region to another is known as thermal convection. This mode of heat transfer is only possible in fluids. We can also visualize thermal convection using a rectangular tube filled with water as shown on your screen. When the loop is heated at the bottom left end, a convectional current is set up in a clockwise direction. We can see this when a colored dye is added at the mouth of the loop. You can see that the dye travels clockwise and not even a little is traveling anti-clockwise. Thermal convection can be natural or forced. If the convection is caused by differences in density due to thermal expansion, then it is called natural convection. An example is what we have just seen. Gravity plays an important role in natural convection, and that is why in natural convection, heating is always in the upward direction. If the container is heated at the top, transmission of heat by convection does not take place in the downward direction. If the movement of matter is caused by a pump or a blower for heat transfer, it is called forced convection. One of the most common examples of forced convection that we see around us is the working of a hair dryer. Air at room temperature is sucked by a motor and heated up by forced convection as it passes over hot coils inside the dryer. This air is then blown out through the nozzle provided. Next, thermal convection in gases. Now, consider this box with two chimneys and a transparent window on one side. A burning candle is also placed below one of the chimneys. As we have seen in liquids, a convectional current will be set up between the inside and the outside of the box. We want to see this convection in air, so we shall use smoke. We place a smoldering piece of paper or stick above the other chimney. You will see that the smoke gets sucked up into the box and moves towards the candle and is eventually expelled out. This happens because the air near the candle gets heated expands and therefore becomes less dense. It therefore rises up the chimney. Adjacent air is drawn in to replace the rising air. This too gets heated, expands and rises. Ultimately, air is drawn in through the other chimney to set up a circulation that we are calling convectional current. Natural convection is responsible for many everyday phenomena. For example, in the coastal areas, wind blows from the sea to the land during daytime. This is known as sea breeze. Sea water warms up much slower than the land because water has high heat capacity. As a result, the air above the land gets heated, expands, becomes lighter and rises, creating a low pressure area. The air above the seawater is drawn to the land to replace the rising air. This onshore airflow forms the sea breeze, which feels like a nice cold wind blowing onto the hot land. At night, the exact reverse happens. Air moves from the land to the sea. This is known as land breeze. During the night, the land loses heat faster than the water, so the air over the water is warmer than that over the land. So it expands and rises, creating a low pressure region. The cooler air over the land is therefore drawn towards the sea to replace the rising air. This offshore wind forms the land breeze. Next is ventilation. This is the supply of fresh air into a room. Air is drawn into the room through windows and doors. This air is consumed by people and is exhaled being warm. It therefore rises up and exits through the ventilation holes near the roof, and more air is drawn in to replace the rising air. This ensures constant supply of fresh air inside the room. A car cooling system removes excess heat from the engine. The system transfers heat from the engine into the vehicle's interior or the atmosphere using heat exchangers called radiators. To perform its job, the cooling system must cool the engine enough to prevent damage while keeping the engine warm enough for efficient operation. The system uses a liquid called a coolant, which may also be water. In the modern water-cooled engines, a pump circulates water through the pipes. Heat is absorbed from the engine. On startup, the water bypasses the radiator to allow the engine reach operation temperature quickly. When the water heats up, the thermostat changes position and allows hot water to flow to the radiator or heat exchanger. An electric fan circulates air around the radiator, which carries away heat from the water and hence cooling it. In the radiator, hot water flows through thin tubes and loses heat to the air circulating through the metal cooling fins, which provide increasing surface area, allowing the heat to be dissipated in the air. In a modern engine, the cooling system is controlled by the electronic control unit ECU, what many people call a car computer. The ECU controls the thermostat and the radiator fan. And finally, radiation. Now, thermal radiation is where heat is transmitted even through vacuum in the form of electromagnetic waves. The electromagnetic waves emitted by a body by virtue of its temperature is called thermal radiation. Heat energy received from the sun is in the form of radiation. Like all electromagnetic waves, thermal radiation can travel at the speed of 300 million meters or 300,000 kilometers per second. All bodies emit thermal radiation. The rate of emission of thermal radiation depends on the temperature of the body. When thermal radiation falls on a body, it is partly absorbed and partly reflected. The amount of heat absorbed by a body depends on its color. Let's see the absorption and emission of radiation. Consider two metallic bars of the same size and material. One is, however, dull in color and the other has a shiny surface. We then stick some wooden stopper on the back of each bar with the candle wax. Then we light a Bunsen burner. We want to see which of the two absorbs heat faster. You will see that the wax on the black painted bar melts fast. And that is because black or dark objects or surfaces absorb thermal radiation faster than shiny ones. This is why we wear white-colored clothes when it is hot and black-colored clothes when it is cold. Again, we have two containers, one dark and the other is shiny. We fill both with hot water. When we dip thermometers, they record the same amount of temperature. After some time, the temperature starts going down as the water loses heat. But the one in the black container loses heat much faster than the one in the shiny container. And therefore, black surfaces are not just good absorbers, they are also good emitters of heat. Shiny surfaces reflect much of the heat of their surfaces. We look at the applications of thermal radiation. The thermos flask is designed to prevent the loss or gain of heat energy by conduction, convection, and radiation. It consists of a double-walled glass vessel. The inner surface of its outer wall and the outer surface of its inner wall are silvered. The space between the walls is a vacuum. The walls are sealed at the top and a vacuum seal provided at the bottom. The glass vessel is protected by encasing it in a metal or plastic case. Inside the case, the glass rests on a cork or a plastic support, which is a poor conductor of heat. The space between the glass and the casing is filled with an insulating material like cork, plastic, or felt. The mouth of the glass vessel is closed with a stopper made of an insulating material like cork or plastic to prevent heat conduction. The metal or plastic case is closed with a cap made of the same material as the outer cover. When a hot liquid is filled into the thermos flask, heat loss from the liquid is minimized as the vessel is made of glass, which is a bad conductor of heat. The insulating material used between the glass vessel and the outer cover prevents heat loss by conduction. The vacuum between the walls of the vessel prevents heat loss due to convection and conduction. The silvered walls of the glass vessel are poor radiators and good reflectors of heat. The heat radiated by the liquid is reflected back into the liquid by the shiny silvery wall. So, heat loss through conduction, convection and radiation is prevented and thus the hot liquid stays hot for longer. Conversely, when a cold liquid is put into the thermos flask, the heat insulating material between the outer core and the glass vessel doesn't allow heat to enter the flask by conduction. Similarly, the vacuum between the walls of the glass vessel and the silvered surfaces do not allow heat to reach the liquid by convection, conduction, or radiation. Therefore, the cold liquid stays cold for longer. Finally, greenhouse effect and heat trap. A greenhouse is used to accelerate the growth of crops and also control environmental conditions. The growth is accelerated by trapping heat inside, which is necessary for photosynthesis. It is made up of transparent polythene material or even glass. The sun's rays penetrate the glass or the polythene. The solar radiation is partly absorbed by the plants and the soil and partly reflected back into the atmosphere. This emitted heat is reflected back by the glass walls, and thus overall the greenhouse remains warm, which accelerates growth of the crops inside.